Good morning and welcome to the lecture series on numerical analysis. In this lecture, we will study about numerical integration. Now, first question arises: why we need numerical integration? So, motivation behind the numerical integration is as follows. If your given integrals are is of this form, integration from 0 to 1 sine of x square, integration from 0 to 2, integrand of this one over dx. It means your integrals are of too complicated and we do not know the analytical methods how to evaluate the integrals. For second case, if your integrand is not precisely defined by an equation, but we are given a set of data values. It means we do not know the exact nature of the integrand, but we are given discrete data values of the function called integrand. Or third case, if you are asked to evaluate this integral without using any analytical calculation. So now next question arises: what is the numerical integration? Suppose this is our integration. So in numerical integration, we approximate the computation of a definite integral using numerical techniques, in which we divide our range of integration into equally spaced subintervals. Now, after simplification, this gives the approximate calculation, which is different from the analytical integral values. Now, next one is numerical integration methods. There are several methods for numerical integration. Out of them, we have mentioned only 4 methods, which are in your syllabus. So first 3 methods, trapezoidal rule, Simpson 1/3 rule, and Simpson 3/8 rules are applicable only for the equally spaced data points, while the Gauss quadrature method is applicable when your data points are unequally spaced. So we study only the 3 methods here: trapezoidal rule, Simpson 1/3 rule, and Simpson 3/8 rule. So first we discuss about the trapezoidal rule. Suppose we are given this integral whose range of integration is x0 to xn and integrand is y. So in trapezoidal rule, first we divide our range of integration x0 to xn into number of subintervals. Suppose here n number of subintervals of equal widths, right? And we replace this our integrand in each subinterval by a straight line. It means suppose this blue line is our given curve of integrand y equals to fx, suppose, and we divide our range of integration x0 to xn into number of subinterval. In each subinterval, we replace this blue line. It means curve y by a straight line zoning the endpoints of the subintervals. So this point is x0 y0, and this point is x1 y1, and this point is x2 y2, and so on. So in the first subinterval, we replace this curve y by a straight line. Similarly, in the second subinterval, we replace this curve by a straight line, and similarly in third and remaining subintervals. So this difference between red line and blue line is the error between the solution, right? So to reduce this error, we minimize the interval width. It means if we minimize the interval width, it means this is our width of the subinterval. Now, if we minimize this width, then we get the more accurate solution, or approximate, actually, or close to the exact solution, right? So in trapezoidal rule, we replace our curve by a straight line joining in each subinterval. So now each subinterval we get a trapezium, all right? In subinterval, this is our trapezium, this is our second trapezium, this is our third trapezium, all right? It means we know that this integration represents the area under the curve. Now, if we divide our range of integration into number of subintervals and we express our curve in each subinterval as a straight line, then we get trapeziums. And in each, and if we sum the areas of the trapezium, then we get the approximate area of the integration of this one under this curve y equals to fx. And we know the area of the trapezium is nothing but 1/2 times of width into height, right? So this is our width, suppose is here h, and this is value of the function here is y0, and here is y1. So area of this first trapezium is h/2 times of y0 plus y1. Similarly, second trapezium area is h upon 2 times of y1 plus y2. Similarly, third and so on. Now, if you simplify or sum the areas of the all the trapezium, then we get this equation number 1, which is nothing but basically the areas of their different trapezium summations, right? So first trapezium rule is given by first equation, which is h upon 2 times of y0 plus yn. This is the value of the function at starting point and end point, and in between points 2 times y1 plus y2 plus and so on. So graphically or geometrically, our trapezium rule expresses is that the curve y equals to fx is replaced by any straight lines joining the points x0, y0 and x1, y1, x1, y1 and x2, y2, and similarly xn minus 1, yn minus 1 and xn, yn. The area bounded by the curve is approximately equal to the sum of the areas of the n trapeziums obtained. It means in trapezium rule, we express this our integrand by a linear function only, right? If we replace this linear function, as we know that to find a linear function of degree 1, right? Because we know that our linear function, suppose ax plus b, then its degree is 1. Now to find the 1 degree polynomial, we need only 2 data points, right? So this is our trapezium rule. Now second one is Simpson 1/3 rule. Now if we replace this integrand y by a second degree polynomial, and we know that to obtain a second degree polynomial we need 3 data points, right? So it means 3 data points means we divide our range of integration x0 to xn in such a way that we get even number of subintervals, right? Because 3 data points means 2 subintervals. So it means in case of Simpson 1/3 rule, we divide our range of integration into even number of subintervals, right? And we replace this integrand by a second degree polynomial here, right? And we simplify and evaluate this integral. For the detailed derivation, you may go through the notes which I have already provided you and simplify, then we get this relation number 2. Now, it should be noted that this rule requires the division of the whole range into an even number of subintervals of width h. Keep in mind here, in trapezoidal rule, we divide our range of integration into a number of subintervals. While in Simpson 1/3 rule, we divide our range of integration into an even number of subintervals, right? And we replace this integrand by a second degree polynomial, while in case of trapezoidal rule, we replace this integrand by a 1 degree polynomial, right? Now next one is Simpson 3/8 rule. Now in this case, if we replace this integrand by a third degree polynomial, and as we know that a third degree polynomial can be evaluated by using a 4 data points. So it means we divide our range of integration, this x0 to xn, as a multiple of 3 subintervals. It means suppose your range of integration is from 0 to 6. Then we divide our range of integration 0 to 6 into a multiple of 3. It means either 3 subintervals, 6 subintervals, 9 subintervals, or 12 subintervals, right? So we divide the range of integration into a multiple of 3 subintervals, and we replace this integrand by a third degree polynomial. And if we simplify, then we get this relation number 3, right? Now, application of these rules. So there is a problem. The cross section of a stream 9 meter wide is measured by means of a soundings taken 1.5 meters apart. The depth recorded are 0, 0.45, 0.6, 1.05, 0.69, 0.3, and 0 meters. The mean velocity is observed to be 1.02 meter per second. Now we have to compute the discharge of the stream. It means there is a stream flow, and the width of the stream is given 9 meter cross section area. All right. So left hand is 0 meter and right hand is 9 meter. And we have taken soundings taken 1.5 meter. It means we have divided our stream width 9 meter into of equals 1.5 meters subintervals, right? It means this is our 0 meter, this one is 1.5 meter, and next one is 3 meter, next is 4.5 meter, next is 6 meter, next is 7.5 meter, and last one is 9 meters. And here depth recorded at 0 meter is 0. At 1.5 meter, it means this is the graphical representation of the given problem. It means depth at the 0 meter is 0. Depth at 1.5 meter is 0.45 meter. Depth at 3 meter is 0.6 meter. And depth at 4.5 is 1.05 meter. And similarly, so on. It means depth at 0 meter and depth at 9 meter are 0. So it means here our argument is depth, and width is our coordinate here. So we use trapezoidal rule here. And we know that in trapezoidal rule, we divide our range of integration into a number of subintervals of equal widths. So we have divided this range of integration. It means 0 to 9. This is our 0 meter and this is our 9 meter. So we divide our range of integration into a number of subintervals of equal width, which is 1.5 meter. And we express our curve by a straight line in each subinterval. This is our 0 meter depth, and this is 0.45 meter depth. So we have joined this by a straight line. Similarly, in the second subinterval, we have joined by a straight line. It means 0.45 meter is joined by a straight line, 0.6 meter. Similarly, and so on. So we have even now we get different trapeziums here, all right? So now if we add some areas of the different trapeziums, then we get the area of the different trapeziums, then we get the cross-sectional area of this section, all right? So cross-sectional area is given by d upon 2 times y0 plus y6 plus 2 times of this one. Here d is the width of the section, right? And y0, y6 are the depth at the different points, right? And this width is given 1.5 meters, and these are the required values. If we simplify, then we get the cross-sectional area is 4.635 meters square. Cross-sectional area means area of this portion below the base of the stream, right? Now rate of flow through the stream is cross-sectional area multiply the average velocity, which is already given, which is 1.02 meter per second. So therefore the rate of flow or discharge of the stream is 4.7277 meter cube per second. So this is the practical application of the trapezoidal rule to evaluate the rate of flow through the stream when we do not know the exact behavior of the stream flow, and we are given only discrete data points, right? Now next one is one more example. A solid of revolution is formed by rotating about the x-axis, the area between the x-axis, the line x equals to 0 and x equals to 1, and a curve through the points with the following coordinates, right? Different values we are given for different values of x and different values of y. Now we have to estimate the volume of solid form, giving the answer up to 3 decimal places. And as we know that if V is the volume of the solid form, then we know that volume is given by pi times integration from 0 to 1 y square dx. Now keep in mind here y square is given, and we know that if our integrand is a second degree polynomial, then Simpson 1/3 rule gives a more accurate result compared to other method. So we use here Simpson 1/3 rule because here integrand is a second degree polynomial, right? If integrand is a 1 degree polynomial, then we use trapezoidal rule. If integrand is a second degree polynomial, then we use Simpson 1/3 rule. If integrand is a third degree polynomial, then we use Simpson 3/8 rule. So here integrand is a second degree polynomial, so we use Simpson 1/3 rule. So first we evaluate the values of y square for different x, right? So for different x, we are given different of y's. So we take the square of each y here, then we get y square here, this one, right? Now width of each x subinterval is 0.25 because equally spaced points are given. So Simpson 1/3 rule is given by this relation. This is pi times this integral is replaced by h upon 3. H means 0.25 divided by 3. This is our y 0 point. It means this one, and this one is end point. This means 0.7081. Now 4 times of even terms and 2 times of odd terms. So these are the even. This is our right. Now if we simplify, then we get 2.819. Now this is our approximate value 2.819, because we are asked to evaluate the volume up to 3 decimal places. So the approximate value is 2.819. One more example, which is the combination of all the three methods: trapezoidal, Simpson's 1/3, and Simpson 3/8 rule. So here range of integration is 0 to 6. So now we use trapezoidal as well as Simpson rules. As we know, that in Simpson 1/3 rule, we need number of subintervals into multiple of 2, while in case of Simpson 3/8 rule, we need number of subintervals as a multiple of 3. So we divide this range of integration 0 to 6 into a 6 subinterval, each of it h equals to 1. So here x equals to 0, 1, 2 up to 6, and the corresponding values of fx. It means fx here is 1 upon 1 plus x square. If you put x equals to 0, then we get 1. X equals to 1, then we get 0.5, and similarly this one. Now by trapezoidal rule, we have h upon 2. H means 1. So 1 upon 2 times, this is our y 0 point, and this one is y 6 point here. All right? So y6 is there, and 2 times of intermediate values. All right? If we simplify, then we get 1.4108. All right? Now to get more accurate result, if we increase the number of subintervals, or we decrease this width h, we get more accurate result. Similarly, by Simpson 1/3 rule, we have h upon 3 here. So h upon 3, this is our y0, this is our y6, plus 4 times of odd terms y1 plus y3 plus y5, plus 2 times of even terms y2 plus y4. And if we simplify, then we get 1.3662. Now Simpson 3/8 rules gives 3h upon 8, right? So 3/8, this is y0, this is y6, and this is the remaining value. Now we simplify, then we get 1.357, right? So thank you for today. In this lecture, we have studied about the numerical integration, and right. So in the next lecture, we study about the numerical solution of the differential equations.